Hello. The second part of our talk about open and closed sets will be devoted to closure, interior and boundary of the set. So we have known space and we have some set in this space. The closure of set A is set of all limit points for A. The interior of A is the set of all interior points of A. And the boundary of A is difference between closure and interior. So it's set of all points from X such what they belong to our closure and they do not belong to interior. Theorem about the closure. The closure of A is the smallest closed set containing A. What does it mean? Actually, it means three claims. First, closure is closed set. Secondly, A belongs to its closure. And third, if A belongs to some closed set, then the same happens for closure. Let's prove it. First, we have to prove what closure of A is closed. We know what closed set contain all. Set is closed if and only if it contains all limit points. So we assume what x is limit point of closure, and we need to prove what x belongs to closure. Well, first, let us recall what it means. It means what x is a limit point of A, so we have to prove that x is a limit point of A. What is equivalent to the fact what ux have non-empty intersection with A for any ux. So this arbitrary neighborhood we will represent as a ball with any small radius. So we fixed some epsilon, and we want to show what this ball will have a non-empty intersection with A. Let's consider the ball with open ball with radius half epsilon, and let denote it as it will be some other neighborhood of x. We will denote it with wave. As x is a limit point of the closure, this neighborhood has a non-empty intersection with closure. That means what there is a point in closure such what y belongs to ball with center x and radius half epsilon. What in its turn means what distance between x and y is smaller than half epsilon. Y is element of the closure. It is by definition of closure is a limit point of A. So y has non-empty intersection with A for any neighborhood of y, and for such neighborhood we can take ball with center of y and radius half epsilon. So there is an element z from A such what distance between y and z is smaller than half epsilon. Now we can estimate the distance between x and z using triangle inequality. And obtain what it is smaller than epsilon. So z belongs to radius or to ball with center of x and radius epsilon. So it belongs to neighborhood or arbitrary neighborhood of x, but it also belongs to A. So indeed the intersection of any neighborhood of x and the set A is non-empty. So we have proven the first part. Second part is obvious. We already admitted what said all points what belong to set are limit points. So set belongs to closure. And the third part, so second one and the third one. Let A belong to some closed set F. Actually to any set F. So if some point is a limit point of A, in any neighborhood there are points of A as a part of F, means what in any neighborhood there are also points of F. So it implies what closure of A belongs to closure of F. But F is closed, means what it contains all limit points. So the closure of F coincides with F itself. So we assumed what A belongs to F, and F is closed, and obtains what sorry, here it's not equal but belong. Obtained what closure of A belongs to F. So this theorem is proved. For interior, we can prove following theorem. The interior of R is the largest open set what belongs to is the largest open set what belongs to A. Once again it means three things. First, interior is open. Second, it belongs to A. And third, let's O open set O belongs to A and O is open. And then O also belongs to interior of A. Let's call it theorem number 2. If you follow the same plan like in previous theorem, you can prove this one. Please do it yourself. And just a few sets about boundary. I remind boundary of A is the difference between closure and interior. What can be represented as an intersection of closure and complement of interior. As an intersection of two closed sets, it is also closed. So each boundary of any set is closed. And last thing about boundary, you can prove, and please we will consider it on the exercises, what the boundary can be represented as intersection of closure of A and closure of complement. So it's a set of points what limit point to both A and the complement of A. So it is actually the same, but it needs to be proved. Prove it, please. So this is all for this paragraph. Thank you very much.